scale there. This is a most colossal structure. The Austrian ethologist Karl von Frisch remarked that if humans built structures on the same scale as termites do, then the structures that we would build would be 4 times as high as the Empire State Building. So termites are very, very impressive architects. These designoid objects are very impressive indeed. We're switching now from objects which are apparently designed by animals to the design of animals themselves, the apparent design of animals themselves. And I'm beginning with camouflage. If you were walking through the desert, you would probably think, to a casual look, that that was a stone. But it's not a stone, it's a grasshopper. It just looks like a stone, and it gets protection from looking like a stone. And in the next example, this looks to me exactly like seaweed. It's one of my favorite of all designoid objects. It is in fact a fish. It's a seahorse. There's its head, there's its neck, there's its body. And these objects sticking out here are part of the fish's body, but anybody would think that they were parts of a seaweed. They look exactly like parts of a seaweed, and the seahorse hides among seaweed of just the right type. It's almost perfectly camouflaged. And we have a few more examples. This is a film of, and you'll see what it is in a moment, it's in fact a leaf insect. There's the shield over the thorax, there's the head, here come the wings, and when it isn't moving, perhaps even when it is moving, it looks exactly like leaves, it's just blown off. Here's another thing, looks just like a plant, turns out to be a green snake. And this, you would think, was a plant with a bud on the end along the green stem. More buds. Only when we get to the front end do we just about spot that it has an eye, antennae, and legs. It is, in fact, a stick insect. Look at these leaves here. Autumn leaves. Look at the vein up the middle of the leaves. Look at the veins on either side. Look at the little splodges of dark-coloured mould on the leaves. But those are not leaves. Those are butterflies. Look there, you can just see the body there, 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 there. That's what these butterflies look like when they open their wings. This is what they look like on the underside of the wings. And they normally sit with the wings folded so that you only see the underside of the wings. And you're very hard put to it to see that they're not dead leaves. Only when they open the wings do you get this flash of brilliant coloration. Camouflaged animals resemble inedible objects. Designoid objects sometimes resemble other designoid objects for other reasons, because they're doing the same job. And this is called convergent evolution. This is an ordinary hedgehog. That is nothing whatever to do with a hedgehog, but superficially it looks like it. That is a spiny anteater. It is a mammal, but you might say only just a mammal. It's an egg-laying mammal, a very primitive mammal, from Australia and New Guinea. As a matter of fact, its way of life is not that close to a hedgehog's way of life. This is an anteater, whereas hedgehogs eat more general things, insects and worms and things. But both of them gain protection from having spiny skins, and so they both superficially look very alike. An example of convergent evolution. An even better example of convergent evolution is the so-called marsupial wolf. Now, if you saw that going along on a lead down the street, you would think it was a dog. A slightly odd sort of dog, perhaps. There aren't many dogs that have quite that structure at the tail end. But you would think that that would not really be out of place at Crufts. But this is not a dog. It has nothing whatever to do with dogs. This is a marsupial. It's much more closely related to kangaroos and wombats and koalas. It's now, most unfortunately, extinct, only fairly recently extinct. It went extinct this century in Tasmania, went extinct some thousands of years ago on the mainland of Australia. And the reason it looks so like a dog is that it does the same job as a dog, or did the same job as a dog. It ran and hunted prey in the same sort of way as a dog does. and that's why it has the same shape as a dog. Okay, perhaps you could take it now, Bryson. Thank you. The structure inside also resembles that of a dog. This is a dog skull, and this is the skull of the Tasmanian wolf. It's a bit larger, but of course the size of the skull will depend on how big the dog is anyway. We could easily get a bigger dog skull than this. The only reliable way to tell that this is a marsupial and not a real dog is if you look underneath. Those two holes in the palate there give the game away. Those are the telltale clues that tell us that this is a marsupial and not a real dog. A real dog doesn't have the same kind of holes there. Well, that's convergent evolution among designoid objects. Designed objects, too, sometimes resemble each other because they're doing the same job. Two aeroplanes closely resemble one another, not because of industrial espionage, not because of imitation, but because the wind tunnel is a great leveler of differences. These planes have both been designed for the same purpose, and when you design planes for the same purpose of flying very fast through the air and carrying a large payload of passengers, those planes are going to come out looking pretty similar. In just the same way as the dog and the marsupial wolf come out looking similar. So we've seen convergence between two designoid objects, and we've seen convergence between two designed objects. How about convergence between designed and designoid objects? Well, here is a camera, which is a designed object. And here is an eye, a designoid object. They both do something very similar. They both have a lens at the front, which focuses an image on a light-sensitive surface at the back. In the eye, it's called the retina. In the camera, it is a film. There are detailed resemblances as well. Both of them have an iris diaphragm, opens and closes to regulate the amount of light that goes in. In an automatic camera, the amount of light that goes in and out is automatically regulated by a light meter. So when it gets brighter, close down the hole. When it gets darker, open up the hole. And the human eye also has an automatic light meter. Now I wonder whether we could have a volunteer to, right, in the front row there, yes. Right. What's your name? Gillian. Now, would you like to take your glasses off, Gillian? Thank you. And come and sit down here, please. Now, what you'd do, please, is look into the camera there, and they're going to take a picture of your eye, of your iris. What I'm going to do is I'm going to shine this light into the other eye. And I hope it won't be too bright. And what we hope to see is that your iris will contract when I shine the light in. So look into the camera, and I'm going to shine the light. Did you see it contract? Look into the camera. There it contracts. Do you see it? I think it's best perhaps to look into the eye that I'm actually shining the light into. And not you. Look into the camera. Is it too bright for you? No. Okay, look into the camera. There it goes. Do you see it? Thank you very much, Daniel. And there are numerous other examples of living things being exactly the way a human engineer would have designed them. Okay, well, I hope that's enough to convince you that there's something special about living objects. They look designed. They look overwhelmingly as though they're designed. I call them designoid, and I asked you to accept this different title. But it's terribly, terribly tempting to use the word design. Time and again, I have to bite my tongue and stop myself saying, for example, that this Swift is designed for rapid, high-speed, highly maneuverable flight. And And as a matter of fact, when talking to other biologists, we none of us bother to bite our tongues. We just use the word designed. But I've told you that they're actually not designed, and coined the special word designoid. And I said that there is a special process that brings designoid objects into existence and gives them their apparently designed look. What is that special process? The answer to this question was discovered surprisingly recently in the middle of the last century. One of the greatest discoveries of all time, made by one of the greatest scientists of all time, Charles Robert Darwin. Quite a surprisingly long time after he discovered his principle of evolution by natural selection, he wrote this famous book, The Origin of Species. This is an original first edition, inscribed by the author. Very valuable. Darwin began his argument on natural selection, he introduced it, in terms of another process called artificial selection, or selective breeding. All these vegetables here have been bred by human breeders for different kinds of food purposes. There's ordinary cabbage, cauliflower, red cabbage, broccoli, Brussels sprouts, kohlrabi. Each of these different sorts of plants has emphasized a different aspect of the original wild ancestor, the wild cabbage. So kohlrabi, for example, has a greatly swollen stem. Cauliflower has a greatly enlarged flower. So does broccoli, but in a different way. They're all descended over the last couple of thousand years from the same wild ancestor, the wild cabbage. Now that's the wild cabbage as grown by Bryson. Bryson has many virtues, but green fingers are not among them. Nevertheless, if you were to take this home and grow it for a little while, water it properly, look after it, it would grow up into a wild cabbage. It wouldn't look very like any of those cabbages. That's the point I'm making. They've all come from the wild cabbage, but they're all very different from the wild cabbage. All the breeds of domestic dogs have been bred from the same common ancestor, namely a wolf. Those dogs look terribly different. You'd never think they were members of the same species, but they all in fact come from the same species, a wolf. Now, how do we get, what is this artificial selection, this selective breeding that enables you to go from a wolf to something like that, or that, or that? Well, I'm going to tell you very, very briefly what it is. You start with your ancestor, the wolf. And I'm going to suppose, for simplicity, that everybody on this side of the room is going to imagine breeding for smaller and smaller wolves, and everybody on that side is going to imagine breeding for larger and larger wolves. So in every litter of wolves that we get, if you're on the small side, what you do is you look out for those individual puppies that are a bit smaller than the average. And those are the ones that you breed from. And on this side, you breed from the larger ones. Now, it's going to take a long time. Generation after generation, you mate together relatively small dogs, wolves, and on this side, you mate together relatively large wolves. And after many generations, perhaps hundreds, perhaps thousands of generations, perhaps a couple of thousand years of this selective breeding, because there are genes involved in controlling the differences between the different puppies, cubs, eventually you may end up with something like what I hope is now going to come in. That would be the end product of breeding for larger and larger sized wolves. That would be something like the original ancestor that you started from, and that would be the end product of breeding for smaller and smaller wolves. What are their names? Jemima and Wilf are Chihuahuas. Jemima is a smooth-haired Chihuahua. Wilf is a rough-haired Chihuahua. And both of them, comparatively recently, are descended from a wild wolf. What's his name? This is Sequin, with a German Shepherd. And I think we could say that Sequin is the one who most resembles the ancestral wolf. And this is Archie, that's a fine name. Archie, a Great Dane, and here's what you get from breeding for larger and larger size, but they're all descended from a wolf, they're all cousins of one another, and Sequin is showing great interest. So thank you very much indeed. Thank you.